Part 2 of lesson 40, the conservation of energy. We just got some more examples here, some different examples than the previous one. Our first one is a toy car with a mass of 212 kilograms is pushed by a student along a track that is moving at 12 meters per second. It hits a spring with a spring constant of 52.8 at the end of the track, causing it to compress. Determine how far the spring compresses to bring the car to a stop. So here's our situation. We have a car, toy car. It's moving along at 12 meters per second. So at this point, it's all kinetic energy. Does it have any potential energy? Well, not gravitational potential energy because it's on the ground. So it has zero gravitational potential energy. What happens to that car? It hits a spring. It's attached to the wall. And then the spring is going to compress. So now the car is here. The spring has compressed and the car comes to a stop. So at this point, the kinetic energy of the car is zero. Where is all that energy gone? It's all been converted into potential energy, but not gravitational potential energy, elastic potential energy. So the EP, it is at a max over here. And before the collision, right up here, the EK was at a max. And the EP, before it hit the spring, the instant before it hit the spring, was zero. So there's our situation. In this case, we have kinetic energy be converted into elastic potential energy, not gravitational potential energy, but elastic potential energy. And we can solve it exactly the way we solved the previous question about the toboggan. The mechanical energy before equals the mechanical energy afterwards. Oops. And because we've done this little diagram right over here, we know that this is zero and this is zero, and therefore we get EK equals EP prime. What is the formula for elastic potential energy? We learned it in one of the previous lessons. That would be 1/2 kx squared. And you'll notice, in this case, the mass does not cancel out. In some previous examples, for example, when we did circular motion or when we did the toboggan going down the hill, the mass canceled out. Why doesn't it cancel out in this case when all of the kinetic energy is converted into potential energy, or vice versa? In the toboggan example, all the potential energy was converted into kinetic energy and the mass became irrelevant. Well, this is a different example. Clearly, if the car had a greater mass, if the car was greater than 212 grams, it would compress the spring more. So the mass is quite relevant in this problem. We're solving for x, the amount that it compresses. So the halves cancel out. And we rearrange the formula to get this. X equals 1/2 mv squared over k. You can plug in the numbers and you end up getting a value of 0.76 meters. So in other words, 76 centimeters, the spring compressed. All right, B is a more realistic question because what it says is, for B, the spring only compressed 50 centimeters. It didn't compress 76 centimeters, it only compressed 50. So what happened? Well, clearly some of the energy was lost. Where was it lost? It was lost in friction or heat and sound. So in the real world, energy is conserved, but in the real world, it's not going to be as easy as it was all converted from this form to this form, or 100% of it. Some energy is going to be lost somewhere. So it's lost in heat and sound. And what we're going to do for this question for B is we're going to calculate how much energy was converted into other forms other than elastic potential energy. So there are multiple ways we can do this. The way I would probably do this question is calculate how much energy it started with, and it started with just kinetic energy. The mass was 212. And if you stick that into calculator, you get 15.264 joules of energy. So it had that much kinetic energy before it hit the spring, no potential energy. Now let's calculate how much potential energy it had when the spring compressed 50 centimeters. One half K x squared, and that gives us an answer of sorry, I'm going to have to do that. 1.5 times 52.8 times 0.5 squared, 6.6. So after the spring had compressed, the car had come to a stop, so now it has no kinetic energy. It's all elastic potential energy, and it has 6.6 joules of elastic potential energy, but it started with 15. So to get how much energy was lost in this problem, we'll just put energy lost. We're just going to subtract those two values. And that gives you 8.6 or 8.7 joules. So in other words, 8.7 joules of energy was lost to friction, heat, sound, other forms of energy. We're not going to be required to calculate exactly how much of each was lost, but that's how much energy was lost in that question. Example 4 is a classic pendulum question, and it's one you've probably done in Science 10. So we won't spend a lot of time on it, but it's also identical to the toboggan problem. So it's the same principle here. We have a pendulum, we let it go. We want to calculate the speed of the pendulum when it gets to the bottom. And all we need to do is acknowledge the following things. At the top here, it is all potential energy. And no kinetic energy. Once it gets to the bottom, the reverse happens. It's all kinetic energy. And no potential energy. Once you've acknowledged that, then it's pretty straightforward. We're just going to do this one very quickly. It's just EM equals EM prime. And we know that all the potential energy gets converted to kinetic energy. mgh equals 1/2 mv squared. The masses cancel out. You get V equals 2gh square root. Plug in your values and get the velocity, and it turns out to be 1.6 meters per second. So there's the velocity at the bottom. More than likely, you're going to get a question like B. Now, this may not be in your notes, so you're going to have to add this to your notes. In B, we want to calculate the velocity of the pendulum when it's 2 centimeters above the ground. So here's the pendulum, starts off being 13 centimeters above the ground. But we want to calculate it when it's, let's say the ground is right here, when it's 2. So just before, there's the bottom, where it's at the bottom, just before when it's 2 centimeters above the ground. I didn't draw this very well. 2 centimeters above the ground right there. What's its velocity? So it won't be going at 1.6, it'll be going something slightly less than 1.6 meters per second, because as in all the potential energy has not been converted to kinetic energy. Most of it has, but not all of it. So we're going to attack that question as we have done similar questions. EM equals M prime. EM before was just EP. For the second half of the equation, the right side of the equation, we need both the potential energy and the kinetic energy, because when it's 2 centimeters above the ground right here, it has both potential energy and kinetic energy. So we need both of those intact. Now, personally, if I've got this specific equation, I'm just going to plug the numbers in and solve for the unknown variable. But if you want, we can manipulate we can solve for the velocity. So we're going to replace this with mgh. mgh prime, because the height is different. This height is 13, this height is 2. Plus 1/2 mv squared, and we're solving for v. And as I go through this manipulation, you'll see why it's probably easier just to plug the numbers in at this point right here and solve for v. It's quite a bit easier. But let's manipulate the formula just so we can go through a few basic math things related to this. So what I'm going to have to do is get rid of, I'm solving for v. I need to get rid of this mgh over here. So I'm going to move it to the other side of the equation. And just be careful here. This mgh over here, and this mgh, this one here, and this one here, you can't just cancel them out. They don't just eliminate each other. Or the m's and the g's, even though because the h's are different, you can't just, the m's and the g's don't just cancel each other out either. And this is, again, why I say this is a difficult manipulation. Then what are we going to do? Then we want to get rid of the half and the m. So we can divide both sides by m. Let's do that. Divide this side by m. Divide this whole thing by m. Now, here's something that's an interesting part of this question. Because there's an m here, 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 and here, these m's actually do cancel each other out. So this m cancels this one cancels this one, and this m also cancels this one. If one of those m's was missing, if, say, for example, this one was missing, then that would not happen. This m would cancel out this one, but you'd have to include it there. So this m, these m's will cancel, these m's will cancel, and you're going to be left with gh minus gh prime. And again, the g's don't cancel, equals 1/2 v squared. Then you're going to multiply both sides by 2. And you're going to get 2 times gh minus gh prime equals v squared. And then you're going to take the square root of both sides. So there's the manipulation of this formula, and it's a tricky one. It would have been much easier for us to just plug in all the values at this point here and then solve for v. But if you want to get into the manipulation, there it is. V equals the square root of that. When you plug in all the numbers, you're going to end up getting 1.47 meters per second. So that is second example. That's more of a physics 20 question that you would get on the conservation of energy. Now, there is one more problem. Should we stick this one in there? Yes, let's just stick this one in quickly, even though it's going to be a very long video. Here it is. This is a great question because it doesn't give you the height, but it just does make you think about physics and math and geometry and trigonometry. And in this example, we're given this angle. We're given the length of the pendulum, and we're going to determine the speed at the bottom. So again, we're going to assume that all the potential energy was converted into kinetic energy. And what the difficulty in this one is we're not given the height. So we have to use some common sense and some trigonometry to find out what the height of the pendulum is at this point right here. H. We don't know. We need to determine the bottom to use this. EP equals, right. We've done this enough that we can just do it quickly. For us to use this formula here to calculate the velocity, we need the height. We don't have it. But our common sense and some trigonometry will allow us to calculate the height of the pendulum, because we know that this is from here to here. Oh, that should be red. Is 0.75, then obviously from here to here is also 0.75. And we know this angle here, let's just do a little dotted line here. There we go. You can probably see how this is going to work now. We want to calculate h. This is h over here. It's the same thing. And how can we calculate h? Well, if we calculate this, I need another color. I'll just do it in blue. If we calculate this, let's just call it x, then h is simply going to be 0.75 minus x. And because we have this right angle triangle now, right angle triangle, there we go. Because we have that, we can calculate x quite simply just using the cosine ratio. And we end up getting that x equals 0.574533. And therefore, to get h, we're going to just subtract that value of x, from the entire length of the pendulum. And that will give us the height from which it started. So we subtract those two values, we end up getting the h equals 0.175467, just to be very precise. In other words, 17 centimeters. 17 centimeters or 0.17 meters. And then we can take this value here, plug it in there, and we will end up getting the answer, which is 1.9 meters per second. Okay, so you can see some different examples of the conservation of energy, and then this last example would probably be considered an HMA question, or a higher level, not an HMA, standard of excellence question. So you really have to use your brain and use some other principles you've learned, some mathematical stuff, but still a great question. And that's the end of that very long lesson. We'll see you for lesson 41, which is power.